Hello everyone, this is Doug, and in this video we're going to talk about Hess's law of heat summation, which is just the idea that if you have a bunch of reactions, you can add up their enthalpies, add up their heats to get a total heat for the total process. But we're going to see how we can use this to solve problems and answer certain questions that we can't really figure out any other way. So remember from previous videos that the enthalpy of a reaction or the heat of the reaction, that's just these delta H values, whether it says heat of reaction, heat of combustion, heat of solvation, heat of formation, heat of whatever, the delta H values is what we're talking about here. And I just have two examples here of making ammonia and burning propane. What Hess's law of heat summation, which is also known as just Hess's law or Hess's law of constant heat summation, it's all the same thing. What Hess's law of heat summation says is that the total change in energy, the total change in enthalpy for a series of reactions is simply just the sum of those individual delta H reactions, those individual delta H values. And what we can do is we're going to use this information about known reactions to deduce information about unknown reaction. So this is the way that you would kind of put it mathematically. It's kind of like Dalton's law of partial pressures in a way, where you have the overall change in energy is just equal to the sum of all the little changes in energy, however many steps you have. So we're saying, and this is not, these reactions are not related, but if these were related, what Hess's law is saying is that if you wanted to find the delta H overall, you would simply add these two up. So if these were related and you added the two up, you'd get 2,312 or so kilojoules per mole, So the Hess's law is just saying, if you have steps that are related to each other, you can just add up those heats to get an overall heat. That's what it's saying. Now, what we're going to do is we get to do, I think this is kind of fun. I think it's kind of like a little puzzle. But what we get to do is we get to treat these equations algebraically. So we get to cancel terms on either side. We get to multiply the entire reaction, and we can reverse the reactions, which reverses that enthalpy sign. So let me show you some examples here. For the first one, we can cancel terms on either side. So that means if you see something like H2, we have H2 on the left and H2 on the right. I have 3 H2s on the left, 2 H2s on the right. So overall, what we're saying is that these two will cancel out 2 of those 3, So now there's only going to be 1 H2 left. And then you would just write the entire equation and say, okay, well, now I only have 1 H2, and I have N2, and I have 2 waters that are on the left-hand side, on the reactant side. And then on the product side, I'd have 2 ammonias plus O2, And that would be the new overall reaction. And you could simply add up this new value. This would have a new delta H value. You'd simply add negative 92.2 and then to 571.6. So we can cancel stuff. And it can be just partials, It didn't have to be 3 and 3. It was 2 and 3, so I had 1 H2 left over. The other thing we can do is we can multiply the entire reaction, but if you have double the stuff, you're also going to double the delta H value, So if you burn twice as much fuel, it's going to release twice as much energy. So it makes sense that if I wanted to, I could take this whole thing, multiply this by 2, but that's also going to multiply this by 2. Or I could have multiplied it by 3 or 4 or 5, whatever the value you want, whatever the value you need. And so if I multiply everything by 2, now that changes this to 6H2 plus 2N2 goes to 3 ammonias. And now the delta H of this reaction here is going to be negative, 184.4 kilojoules per mole. So you can multiply these whole things as you need, as you're figuring out these puzzles as you need, so that you can get things to cancel out and make sense with whatever it is you're looking for. So you can multiply them up. The last thing you get to do is you can reverse the reactions, but anytime you reverse the reaction, you're going to change the sign, Keep in mind that if a reaction went downhill, so you had negative 10, if you do the same reaction but you go uphill, that's going to be positive 10, So it's the same, if it's the same reaction and you just reverse it, then it's going to have an equal and opposite energy here. So if I take this and I just reverse it, so I'm going to flip this. So now I'm going to say, I have 2 ammonias turning into 3 H2s and 1 NH2, one nitrogen. Now the delta H of this reaction is simply 92.2 kilojoules per mole. You just flip it. It's the opposite value. Instead of going up that hill, you're going down that hill, or vice versa. So these are the 3 operations that we're going to need to do when we approach Hess's law type of problems. So this first one, right, keeping in mind that we can cancel terms on either side, we can multiply entire reactions, and we can reverse reactions, which changes the sign of that delta H value. So first example, I want to find the heat of the reaction using these heat of formation values, right? So I want to find the heat of the reaction of this following reaction. I've got carbon disulfide, 3 oxygens make carbon dioxide, and 2 sulfur dioxides. I want to know what's that heat of reaction. And I'm giving you these heat of formation values, right? Which again, you can just look up online or in a book. So what I'm going to do is I'm going to write out these heat of formation reactions, right? I'm going to write out the heat of formation for carbon dioxide. Apparently that value is negative 393.5, and that's kilojoules per mole. I'm not going to write it over and over again, but the units are kilojoules per mole. And I remember that my heat of formation reactions, right, those always come from the pure elements. So this full equation is 1 carbon plus an oxygen makes carbon dioxide. I'm also going to do it with my CS21, which had a delta H value of 87.9. And that came from a carbon and sulfur, but remember sulfur was S8. Since I only want 2 sulfurs, that means I want a quarter of this S8, right? Because I want 2 sulfurs, not 8. And then lastly, the SO2, apparently that delta H is negative 296.8. To get SO2, I have a sulfur, which is S8, and I add oxygen, which is O2, but I only want 1 sulfur in this case, so I need 1/8 of the S8, and then 1 O2 molecule makes SO2. So what I'm trying to do here, right, is that this is my goal. I'm trying to rearrange these 3 equations that I drew in black here so that it looks like that overall equation, right? This is what I'm looking for. So what I'm going to do is I'm going to take these and I'm going to start flipping them around. So I'm going to kind of draw a line. I've got all of my information here. I'm going to draw a little line here and arrange things how I need. So for example, I see that I need CO2 as a product. So for my equation where I have CO2, it is a product. There's only one of them. So I'm just going to simply rewrite that down here. Carbon plus O2 goes to CO2. And that delta H value is still negative 393.5. I didn't flip it. I didn't multiply it. I didn't do anything. But if I look at the CS2 one where I made carbon disulfide, that's a reactant. That's not a product. So what I need to do with this equation is I need to flip it, right? Because I need the CS2 to be on the reactant side. I'm trying to get all of these to rearrange so they look like this equation. So I'm going to flip that one. So what I'm going to do is I'm going to take this reaction and I'm going to flip it. I'm going to flip this one so that now my CS2 is a reactant. Carbon now is a product. That 1/4 of my S8 is now a product also, and my delta H value is now negative 87.9, right? It was positive 87.9, but because I reversed the reaction, I now have the opposite, right? So the opposite reaction, so it has the opposite value for its enthalpy, for its heat. And then if I look at my last one where I made the sulfur dioxide is a reactant, so that's good. I don't need to flip it. But in this equation, it has 2 sulfur dioxides, and I only have 1 sulfur dioxide. So what I'm going to have to do for this one is I'm going to have to take this one, and I'm going to have to multiply it by 2. I'm going to have to do times 2 here. And when I mean times 2, I mean times 2, right, to everything, the whole shebang. So times 2 to everything. So instead of 1/8 of an S8, now I have 2/8 of an S8. Instead of 1 O2, now I have 2 O2s, and now I have 2 SO2s. But since I doubled everything, it makes sense, right, that I should double the amount of energy that gets released by this. So this is now 593.6. Right, if we double that up. And so now I've arranged everything so that all the parts are in the right places. And my last job here is to simply do all of this canceling out, right? I haven't canceled terms out on either side yet. So if I look at this, I see that I have a carbon over here on the left as a reactant, but I also have carbon over here on the right as a product. So nothing really happened to it, right? I started with carbon, ended with carbon. So that means I get to cancel it out, just like you would if these were variables in an algebraic equation, right? Where the arrows were equal signs instead. If you look carefully, I can do a little bit more here. I have a quarter of an S8, and 2/8 is the same as a quarter, right? So I have 2/8 of an S8 and 2/8 of an S8. So I can cancel those out too. And then I don't think I can really cancel anything else out here. All right, so I'm left with a carbon disulfide as a reactant. I have 1 oxygen, and I have 2 more oxygen molecules, so 3 altogether. I have a carbon dioxide, and I have 2 sulfur dioxides as products, plus 2 sulfur dioxides. And that is this equation that I had up here, right? That was my goal. That's exactly what I wanted this to look like. 1 sulfur dioxide, 3 oxygens, plus a CO2, and 2 SO2s. So that means now all I need to do to get my delta H for this whole reaction is simply add these up, right? So I'm literally going to take negative 393.5 plus negative 78.9 plus negative 593.6 to give me a grand total of negative 1,075 kilojoules per mole. Right, and I put kilojoules per mole, right, because that was the units that we were talking about here. So that would be my product. That's how I'd figure this out, right? That's what Hess's law helped me do, was it helped me figure out what the heat of this reaction was, even though I didn't use a calorimeter. I just used these delta H values. And we kind of talked about using delta H values before. You could have done this a different way, but here's one way using Hess's law to figure this out. So let's look at this one. Here's another example, right? Another Hess's law one. Here we're going to find a heat of formation using other enthalpy values, using other delta H values, right? So I'm giving you 3 pieces of information here. I'm giving you that the overall heated reaction for this reaction, where I take 2 C2H2s and I add 2 equivalents of HBr, and I make that total heat of reaction is this. And I'm also giving you heats of formations of these. And what I want to know is, well, what's the heat of formation of just that product? What's the heat of formation for the C2H4Br2, right? Because this is not the heat of formation of it. The heat of formation, remember, just comes from pure compounds, right? It should be C's and H's and Brs here, not this HBr, not this C2H2, whatever that is. So this is not the heat of formation reaction. I want to know just what's the heat of formation of that thing. So let's get our information together. I've got my overall up there. I also have here HBr. I've got my HBr, so let's write this. I've got HBr apparently has a heat of formation of negative 36.2, again, kilojoules per mole. How did that get made? Well, you take H2 and you take Br2 to mix those up, but I don't want a whole Br2. I just want a half of Br2 and I want half of an H2. And then I also have this C2H2, and apparently its heat of formation is 226 kilojoules per mole. How am I going to make C2H2? Well, I've got carbon, I've got hydrogen. I need, okay, so 1 H2, and then I need 2 carbons in order to make that. So that's that equation. And they're asking me to find what I don't know. What I don't know is this, right? They want to know what's the heat of formation of this sucker. We don't know. But I can write the equation for it. I do know that it's going to be 2 carbons, and it's going to be 2 H2s, and it's going to be 1 Br2. Right? And then I have my overall equation here also. So what I'm going to do is I'm going to try to rearrange these so that they look like the overall equation, and then I'll be able to deduce what the heat of formation is here, because we'll see how much more heat is needed to get to that value, right? It's going to be some sort of sum of these to get to this value, but I don't know what this is, so I'm just going to be like solving for an unknown, solving for x. So let me show you kind of how we go about that. So similar ideas. Bromine, or sorry, the hydrobromic acid, the HBr, in my equation, it's on the right, and there's only 1 of them. What I need it to do is I need it to be on the left. I need it to be a reactant. I need 2 of them. So I'm actually going to take this, right? Let me draw this little line again. Right, here's my info. I'm going to take this, and I am going to flip it and double it. So I'm going to flip and I'm going to multiply it by 2. So now I have 2 bromines as a reactant, sorry, 2 HBRs as a reactant. And now I have an H2 molecule and a Br2 molecule. And my delta H value is going to be doubled and positive, right? So now it's 72.4 kilojoules per mole, right? So I doubled the negative 36 to get negative 72.4, and I changed the sign because I had to flip the reaction, right? So I did 2 operations on that. I flipped it and I doubled it. And again, I did that because I want 2 HBRs as reactants. So I made it so there's 2 HBRs as reactants. Here I have C2H2 as a product. I want it to be a reactant, so I need to flip that. So we've got C2H2 goes to 2 carbons plus an H2. That delta H simply changes signs, so negative 2 to 6, because I just flipped it. I didn't multiply it by anything. And then for my last one that I don't know anything about, this is the product here. That's the product there. So I don't really need to do anything to that. I'm just going to redraw it. So I'm just going to put 2 C's plus 2 H2s plus Br2 goes to C2H4 Br2. But again, right, the idea is that I don't know what this is. You can put a question mark. You can put an X if you like to solve for X. But I do know that if you add all of this stuff up, right, this is Hess's law of heat summation, if you add all this stuff up, you can just double check that the right things cancel out, right? So it looks like I have, let's see here. I've got 2 carbons on the left, 2 carbons on the right. They cancel. I've got 2 H2s on the left, and I have 2 H2s on the right. Those cancel out. I've got a Br2 on the right and a Br2 on the left. Those cancel out, which leaves me with exactly the formula that we were supposed to get. I mean, the equation that we were supposed to get, which was C2H2 plus 2 HBRs. It's the only thing that's left over on the reactant side. Goes to C2H4 Br2. But I do know this, right? I do know that this heat of reaction is negative 198.2. So remember that Hess's law, right? Hess's law is saying that your H overall, right? The overall change in heat is simply the heats that you add up from the individual steps. So we can even think of these as like being H1, H2, H3, right? We're going to add up those 3 to get the overall, right? This is the overall. And I can just put all of those numbers in, right? So negative 198.2 is going to equal 72.4 plus negative 226 plus, we don't know, right? We don't know what this other one is. Again, you could have called it X. I'm calling it H3. We don't know what it is. But then you just solve, right? You just solve for delta H3. I ran out of room, so I can't really show that last little bit. But then you should find that your delta H3 is going to equal 351.9 kilojoules per mole. So again, nothing too crazy here. This is just algebra we're doing, not crazy math. But we were able to deduce, thank you to Hess's law of heat formation or heat summation, we're able to deduce what the value of this heat of formation is, right? This H3, this is the heat of formation for that step, right? This is what we're looking for. The heat of formation for that step. So now, even though I didn't do calorimetry, I didn't do anything weird like that, I wasn't able to find this delta H value in a book, I was able to figure it out using other information I know. Now for this last one, it's a little bit shorter. I'd like you to pause and take a crack at this one, right? So I'm giving you a couple of equations. So here we're going to find a heat of reaction using other heat of reaction equations, right? So we're really just summing up these heats of reactions. So I gave you these 2. I need you to manipulate them so that you get this, so we can figure out what its heat of reaction is overall. So pause, see what you can do. Okie doke. So I'm going to rewrite. Well, I don't even have to rewrite these. If I look at this, right, I'm trying to get everything to look like it does here. Water, I see in this first equation, is a product, but I don't want it as a product. I need it as a reactant. So I'm going to take my water and I need to flip it and multiply it by 3 because I need 6 waters, not just 2. So I'm going to take this, I'm going to flip, and I'm going to multiply everything by 3 so that I get 6 waters. I get 6 waters, I get 6 H2s, I get 3 O2s, and that's going to change my delta H value, right? It's going to be flipped, so now I know it's positive. And it has to be multiplied by 3, so that's going to be 1,714.8 kilojoules per mole. And then for my second one, I see that I have C6. This looks right? I want this C6H6 on the reactant side, but it looks like I need 2. So I need to just double that one up. So this one, I'm just going to double. I'm just going to go times 2. All right, so I'm going to double all of that stuff. So now I've got 2 C6H6 plus 6 H2s go to 2 C6H12s. And again, that value is going to be multiplied by 2 because I doubled everything. So that's going to be negative 412.2 kilojoules per mole. Let me check my work. What do I have that cancels? I've got 6H2, those cancel, right? The top one, this is on the product side, this is on the reactant side. Sorry, I didn't line up my arrows very well, but that's still the product side, that's still the reactant side, so they cancel. And I think that's really it. That's the only thing really, right, that cancels. So redraw my overall equation, make sure that it matches. So now I have 2 C6H6s plus 6 waters goes to 2 C6H12s and 3 waters. Not waters, oxygens. So now I can just simply add up all of this stuff to get my overall delta H, which should be 13,002.6 kilojoules per mole. Right, that is the heat of reaction that we were looking for. That's the heat of reaction of the whole thing. I just added up individual reactions stepwise. So I hope you have a better idea of how to use Hess's law, what Hess's law is all about, and how we can figure out unknown enthalpy values, unknown heat of whatever values using this. And again, it's not like you can only use this for heat of formation or heats of reactions. It's any enthalpy value at all, right? It's Hess's law of heat summation, so heat of whatever you want. Anything, any subscript for that delta H value works great. So practice this up. Let me know if you have questions. Good luck.